I've got a glass of water here. I'm going to do something rather interesting with this because I told you yesterday that there's one thing for talking about what happens if I increase the temperature or decrease the temperature of the water, because we're so used to seeing it. We see it in the refrigerator, the freezer every day, and we see it on a stove every day. What's going to happen? But we don't have one of these every day. We don't have a vacuum pump. Now, you've seen the vacuum pump work before. You know what it does. It sucks air out, decreases the pressure inside of this container. All right, this bell jar I'm going to put on here. Now, I want you to watch what happens. It's stable enough there. Watch what happens when I turn this guy on. Okay. Now, pay attention. I'm going to move the camera over to it a little bit and show you what's happening up close for those people at home. Anybody at home today? Missing anybody? No. The other class, we're missing Jackson. This one goes out to Jackson. So, now Jackson's going to watch this, and so is everybody else who's absent. If you look at this guy up close, Jackson has the best seat in the house. You're going to start seeing something happen to that water. You guys will all see it in a little bit, even from where you are, in a minute. Right now, if I'm looking real close, I'm seeing little tiny bubbles forming in there. Tiny bubbles.
And they are brought to you by Dale's Bakery.
In the wine. That's Don Ho, the wine singer. Well, anyway, look at those tiny bubbles forming. Interesting. Very interesting. But keep watching, and we're going to see those tiny bubbles are getting bigger and bigger. And it's, what? What is it doing? It's boiling. I am boiling water. Wow. That is pretty amazing. Now I'm going to shut this guy off, put it back down. Okay. I boiled water. So it's hot now, right?
Sure. It's probably cold.
What?
Is it cold?
We all know how you boil water. Even Emily knows. She works at a bakery. How do you boil water, Emily? Yeah. Boil it on a stove, so it must be hot, right?
Well, I do it over fire.
What?
Oh my God, is it cold?
Is it hot?
Hey, girl.
It's not hot. All right, we got to explain this. Because you could have, no one here would have had a problem saying, if I said to you, well, we're going to put water on a stove. What's it going to do? Freeze, condense, or boil? You all would have said boil, put it on a stove. But when I said I'm going to put water in here, not many of you knew which it was going to do. And the reason for that is that you don't deal with volume and pressure changes all the time. And that's what we're going to have to learn, how to be able to predict this. Okay, so get your notes out and watch this.
Please tell me.
Yelling at my dog in my high-pitched voice. So, who cares? Did you win or you? I don't know. Evidently, yes. You're doing pretty good for killing most of my brain cells.
All right, I need your attention. Take a look up here.
I'm not failing anything.
Okay. Let me explain to you, in terms of the Chateliers principle, what happened. This is what I need to be able to do. I need to be able to predict this. I'm telling you right now, guys, I've just been grading these papers. You're getting the same paper in about, maybe 5 or 10 minutes after I explain it. All right, one more time, and kind of review with you the other one from yesterday as well. You're getting these papers, and you're going to have about 20. It's going to take you about 20 minutes because some of them are scenario questions. I need to go over a little bit with you. All right, when I say scenario questions, I mean kind of like what I talked about yesterday. We were talking about why does sweating cool you off? All right. Well, today it's going to be about pressure and volume changes, which are not so easy. All right. Let's take a look first of all of what we saw here. Okay. Actually, you know what? I'm going to actually do them a little out of order. I'm going to do. Hold on. I'm going to do this guy first. All right, it's kind of review from yesterday with you. All right. I knew it. All right, let's review from yesterday. Okay, you watching? This is from yesterday. We actually copied 3 different versions of this jar into your notes. Now let's see what happened in those versions, okay? First of all, we have an evaporation and a condensation going on. It's at equilibrium. Here's my jar. It's just sitting there, okay? It's happy. Okay. I come along and I increase the temperature. You all tell me what's going to happen if I increase the temperature. I'm going to favor evaporation. Now, the reason you know it favors evaporation is twofold. One, you've all heated up water, and you know it's going to evaporate faster if you heat it up. But there's another reason that I'm going to favor evaporation, okay? It has to do with the equation, okay? Remember what the equation looks like? Let me get to the end here. The equation's right there, okay? I tried to explain to you how it favored evaporation because what you were doing was adding energy. You made this side too heavy. Let's go back to my balance. Okay? Remember the balance. If it's sitting there, all happy, right, and it's balanced, and I go and I make this side too heavy by adding energy, made this side too heavy, I got Stosh and Stan running back and forth between here. One of the guys is going to work faster than the other one to bring them back to equilibrium. Who's got to work faster if this side's too heavy? Guy going forward, right? So it's going to favor the forward. We all agree that it favored the forward. Okay, so let's go back to that in a second here. So your first effect is to favor the forward direction. You get more evaporation than condensation. Now, after a while, you're getting more vapor molecules. So you're getting more condensation. That's creeping up until eventually it will reestablish equilibrium, but there are more molecules in the vapor phase. Now, we're able to predict that one for two reasons. We looked at Le Chatelier's principle. Basically, which side's heavier, it's a balance. But mainly we're able to do it because we all know that, heating water up makes it boil. And I boiled water yesterday. You remember me doing it over here in that paper cup. Okay. But today, not so easy. Okay? Let's go back today. We already did that one, didn't we? Hold on. This is what I want. All right, so today, this is what we did. And I could do it with a syringe as well. Okay, let's take a look at how I do this with a syringe. If I have my syringe here, and I did talk about this yesterday a little bit too, right? You took notes on it. Did you draw these syringes yesterday in your notes? Okay, good. Now I pulled it back on the syringe, and what's happening to the size of the container? The container's getting larger, the same number of particles, which means basically you've got a lower concentration. And that's what I did back in there. I sucked out vapor. Okay, if I look at this guy, he kind of would look like this. Let's draw in some vapor molecules. He's sitting here, and I'll draw in 10. Now, when I pull back, when I decrease the pressure, I have those same 10 molecules, but now they're all spread out. Okay? Higher concentration here than there is here. So what I was actually doing, remembering this equation, liquid plus energy yields vapor, is in effect, pulling back on that equation didn't really affect the energy, didn't really affect the liquid because liquids are not compressible. What it really affected was the vapor. And I was removing vapor. Wasn't I? So I'm going to favor evaporation to try to get that vapor back. That's what Le Chatelier's principle says. And you can see just common sense says, assume that the rates of evaporation stayed the same. That arrow's the same size. Now that I've got only that many molecules there, all right, the concentration's less, the rate of condensation is going to be less, right? Until it eventually goes and reestablishes equilibrium. Why will it reestablish equilibrium? Because if I've got more evaporation and condensation, what's going to happen over time to this guy? More and more until it gets to be the same concentration as it was before, and that arrow creeps back up, and they're both the same height again. All right. So why did water boil when I was able to put it into, and without adding any temperature to it? Because I was favoring the forward direction so much more than the reverse. Boiling is just when the pressure above the water is equal to the pressure of the water trying to evaporate. Normally, here's how you do that. Normally, you want to boil water? You make this arrow bigger. You make that arrow bigger to make the pressure of the liquid water evaporating equal to the pressure above it. But I didn't do that. Instead, I let that arrow stay the same, and I removed the pressure that it had to overcome. And that's why, if I go to a mountaintop, I go on top of a mountain, and I boil water, and I drop an egg in there. Is it cooking at the same temperature that the egg's cooking down here at sea level? No. it's actually at a much lower temperature up there, depending on how high the mountain is, because there's less pressure. If there's less pressure at the top of the mountain, hey, if I try to boil one in there, if I drop my egg into that bell jar while it's boiling, that water is boiling, how long is it going to take to cook that egg?
A long time.
Forever. Right. It's going to be room temperature. It's never going to cook. All right. So that's why, all right, pressure, that's how pressure, I should say, affects the boiling point. Okay? And that's why I was able to boil water. I boiled it not by making this arrow bigger, not by making the water evaporate so much faster, but rather by making the pressure above it so much less, by removing the vapor, removing it completely so that the evaporation is happening spontaneously versus the amount that's actually recondensing. Now this helps to explain another one of the scenario questions you're going to get in just a minute on your papers. Okay? All right, let's talk about some of these scenario questions. But before I do, I just want to make sure I did give you guys all the notes on well, we didn't do vapor pressure yet. But I gave you all the notes here, these notes here. Let me show you. On pressure and volume. You already, I just want to make sure I did that with this class. All right, good enough. All right, let's talk about this worksheet then, because that's what you're going to be doing. It's going to take you about 20 minutes to get done. How much do we have? About 30. So I have about 5 more minutes. I could get you prepared for this. All right, let's talk about it. What are some other scenarios I've been talking about? Well, how about a pressure cooker? A pressure cooker, how does that work? Does anybody know what a pressure cooker is? No, a pressure cooker does not suck out things. A pressure cooker increases, you put a lid on, all right? So it increases the pressure above, all right, kind of like if I push down on this. Now, I want you to think about what would that affect? Would it make it easier or harder for it to boil? We saw what happened when I sucked air out, right? When we suck vapor out. Is it going to make it easier to boil or harder to boil? Harder, which means if I'm in a pressure cooker and I drop my egg in there, it's going to cook a lot faster because now it's not cooking at 100 degrees Celsius, which is what boiling point of water is. It's cooking at a higher temperature than that. Just like when I drop my egg at a mountaintop, it's not cooking at 100 degrees. It's cooking at a temperature below that because it's a lot easier for it to boil. Okay? All right. Why? Because I've changed the pressure above it. All right? By changing either the volume or whatever. So that's a good scenario question you're going to see on the worksheet. Did I talk about humidity? How that works? Yesterday. I don't think we did, right? Let's talk about that one.
Yes, you did.
Well, even if we did, because I know it's on the sheet. It's on. You have 2 sheets you're going to be doing, and it's on one of them. So let's talk about that one right now. All right. Wow, that's pretty amazing. Okay, I'll accept that. Here, water on your skin, dry day. Water on your skin, humid day. Kind of has to do with what we just saw a minute ago. Okay, and here's your equation. Liquid plus energy yields vapor. Now, first off, let's explain why sweating cools you off. In both days, water is evaporating off your skin. So we'll draw an arrow, and let's say it's 90 degrees on both days. So it's evaporating off your skin about the same amount in both days. But what's different about the dry day versus the humid day? What's different? I haven't drawn, what have I not drawn in here? The condensation. Is there going to be a lot of condensation on a dry day? No. Okay. But there's going to be a lot more on a humid day. Now, why is it that sweating cools you off? Because as you sweat, water goes out from your body onto your skin. That water evaporates off. Evaporation takes energy with it, right? You see it? Takes energy with it and turns it into vapor. So it's cooling you off by removing that energy from your body. On this day, your net evaporation is not very high, is it? Compared to how much you're condensing over here. You're condensing a lot more back onto your skin over here. Another reason why when you talk about, I think I mentioned this yesterday too, I'm not sure, what you're most likely on a humid day, you're more likely to suffer something like heat stroke, where your body can't cool itself off, right? On a dry day, you're more likely to suffer what? Dehydration, where your body, you kind of feel okay, you know, because your body's able to cool itself off, but you're losing tons of electrolytes and tons of water, okay? All right, so there you go. That explains that one, scenario questions. Some other questions. I'm going to drop spaghetti into a pot of boiling water. Well, first I'm going to put the pot of boiling water on a stove. Same exact amount here, and then I go to Mount Everest and do the same thing. Which one's going to get to its boiling point first? Mount Everest. It's going to get to the boiling point first. Because why? Because there's less pressure, and therefore the boiling point is lower. Okay. Now I drop the egg into both. Which one's going to cook faster? Yeah, one at sea level. It would take longer to cook it, the one up the top of the mountain. All of these are questions you have to be able to answer. All right, when I ask these, because that's the kind of questions I'm giving you on here, and not just in one word or one phrase, but rather in a couple of sentences. All right, so just so you know.